Quantum computing is viewed by many as some mystic, far-off, strange, incomprehensible thing that no one understands. Or it's viewed as the next revolution of the computers everyone has in their home or phone. Hi, my name is Rolf Segers, and in this 7-minute video I hope to give you a different insight in how you should view quantum computing, and I'll do this by using two analogies: soap bubbles to show you how you should view quantum computing, and toddlers to show you the challenge quantum computing faces. I will close this video by showing you the different types of qubits that are currently being researched. Right, let's start with the bubbles. Imagine you have this foundation for a building. Think of a set of steel poles connected together, and you want to make a sturdy building out of it. But you want to use as little material as possible. Obviously you can calculate this through optimization, but you can also apply physical phenomenon to it, specifically this. Behold the Q bubble of architecture. A soap bubble has the property that, given a volume, it will always form the smallest surface area that fits that volume. In short, you can use a soap bubble as a physical calculation for that architectural problem. How? Simple. You dip the frame into a tub of soapy water and voila, the solution. And in case you're wondering, yes, there's a real-life example: the Olympic Stadium in Munich. In 1972, Fry Otto used the aforementioned Q bubbles to calculate this design. And here lies the first essence of quantum computing. It is not a classical computer like the one you're sitting behind right now. It is a physical or natural phenomenon suitable to solve very specific physical problems. Through various interesting tricks, very difficult problems can be converted into the correct wire structure, onto which you then release the qubits, or in this example, Q bubbles. Let them do their thing and then study and use the outcome. Okay, next, toddlers. See here a set of qubits, and here one qubit is represented by one toddler. The challenge: a 100 qubit system can be compared to 100 toddlers. Individually, they don't really pose a challenge. You put them in a class and you close the door. But you want to study the changes in the coherence amongst the toddlers. This means you have to get those toddlers to hold hands with each other, and once they do that, they are, in quantum language, entangled. The duration they manage to hold hands, or in other words their attention span, is called coherence. And just as you have to release the aforementioned Q bubbles onto a wire structure to do the calculation, you have to send these toddlers through this obstacle course and then analyze the end result. Another problem is that most of these experiments currently take place close to absolute zero, a few millikelvins. You could call this the natural environment of an experimental qubit. In analogy, this would be the natural environment for a toddler. Hence, raising the temperature for your experimental qubits from millikelvin to few Kelvin would mean a temperature increase of a factor 1000. To give you an idea what that would look like for our toddlers, you can imagine that they will have some issues holding hands in that environment. By the way, in this analogy, going to room temperature environment for experiments on qubits would roughly look like this for toddlers. Another big challenge is stability. Because everything happens on such a small scale, stability of the individual qubits is also a challenge. So, last part. What type of qubits or toddlers do you actually have? Well, there are many types of toddlers and there are many types of qubits. I'll mention the 4 most well-known currently. The most conventional and currently best-known qubit is the superconducting qubit, also called the transmon. This is the most researched and is now being used by companies like Google, IBM, Rigetti in the US, and IQM and Quantware in the EU. This qubit has been used in the quantum supremacy experiment. The advantage? Quite well known and fast. Problem? Requires low temperatures, as I showed you, and has a short attention span or coherence. Then there are the more recent experiments on ion traps, which use atom molecules with a charge. Think of statistically charged toddlers. Companies working on this include IonQ and Honeywell. Advantage: potentially longer attention span or coherence, and potentially more stable. Downside: slow, and one trap can only hold a limited amount of qubits. Then there are the photon qubits, being developed by companies like Quix Quantum, Xanadu, PsiQuantum. Downside is technically not much is possible yet. The advantage, however, it's ideal for communication, and more importantly, they work at room temperature, which for toddlers would look like this. And finally, spin qubits. The special thing about these is that they remain stable at a relatively high temperature. Where the conventional qubits currently work in millikelvin environment, these spin qubits can work in a Kelvin environment, so roughly a factor of 100 to 1000 warmer environment. These qubits are currently being developed under the QTech banner by both TU Delft and TNO. The takeaway from this lecture: quantum computing should not be compared to a classical computing machine. A quantum computer is a physical system which you can analyze and or mimic certain phenomena. Think of soap bubbles. The second takeaway is that the conditions under which these qubits must operate are far from ideal. And it's damn difficult to keep 100, let alone 1000 toddlers in line while they're holding hands, taking an obstacle course in a volcano. I hope you enjoyed this video. My name is Rolf Segers and I'll see you in the next one.